of schedule, which is ironic because I just arrived here. So first of all, let me apologize to all the speakers from yesterday. I had some visa issues, so I had to delay my flight until this morning, and I really just flew in. I have a lot of slides, but I'm highly caffeinated, so I think we can get through them all in time. Thanks for awesome Vietnamese coffee. All right, so my name is Zan Peeters. I work at Asia A in Taiwan, Academia Sinica. Also, please note the second person on the list here is Kota Naito. He will be the next speaker, and he's my master's student. So if you pay attention in my talk, it will be easier to understand his talk as well. The other people in our group are Silver. He's a new postdoc. I'm training him to learn how to use the nanosims, and Typhoon Lee, who many of you may know as a geochemist and a cosmochemist. Okay, so we work in, like I said, in Academia Sinica, and we operate the Nanosims lab. Academia Sinica bought a Nanosims a few years ago, and we're operating it. All right, so astrobiology. We have to start here with this picture. Many of you have seen this picture before. It kind of encompasses everything that you know is astrobiology. It has stars, it has planets, it has small bodies, and it has molecules, because it's basically the chemistry that takes place during the life cycle of a solar system. So the main thing here is that we're talking about carbon. Carbon is the most versatile element in the periodic table, and it's the one that does all the chemistry of life. So what I'm interested in is the building blocks of life. Before you can form life on Earth, the building blocks have to come from somewhere. So this is one of the 4 elements that Ramon mentioned in the previous talk. So prebiotic molecules. I'm sure everybody knows about this. You can take a meteorite, a carbonaceous contrite, crush it, dump it in water, extract the water, run some analysis, and you'll find a whole host of interesting molecules. And to me, this is why I got interested in astrobiology in the first place. It's the realization that if you look at a meteorite, a rock from outer space, and you find the same building blocks as all of life is made up of, that's got to make you wonder. That gave me goosebumps, and that's why I decided to do astrobiology. So this is great. This is just a typical list. This is by no means exhaustive. The list is much longer than this, and many other. I don't do this, but many others have done this kind of research. So that's fun. We have these prebiotic molecules available in meteorites, but to me, there is a big elephant in the room. The majority of carbon is locked up in a macromolecular network. It's not in the form of, amino acids or nucleobases or what have you. It is a large kerogen-like material that is a macromolecular network. It's not soluble. And that's the majority of where the carbon is locked up. So that is what I focus on in this talk, and that's what my research is all about. Okay, so where does this come from? And I think this has been talked about yesterday as well, so I apologize if I duplicate some stuff here. One suggestion for where this may be formed is grain chemistry in a cold cloud, maybe the cloud that ultimately formed our solar system. So you have a bunch of grains in a cold environment. So there's an ice layer. Ice is mostly water, and it has some other molecules in it, maybe methane and ammonia, and what else have you? CO2. There's impact from UV and cosmic radiation that creates radicals, and those radicals form small molecules. Now, when this happens at low temperature, chemistry does occur, and you do form small molecules such as methanol and aldehyde and methylamine and a whole list more. This is a whole field of research that has been done by others and by myself in the past as well. But then you warm up the ice. You go from maybe, say, 20 Kelvin up to 50, 60, 70, or 100 Kelvin, and the ice starts to sublimate. And when the ice starts to sublimate, all of a sudden, all these radicals, which were pretty comfy sitting in the cold ice, all of a sudden meet each other and start to react like crazy. So what happens is you get some sort of intermediate polymer, and that continues on, and with a little bit of aqueous alteration and thermal alteration, you get some kind of large crust. If you do this experiment in the lab and you look at your sample window, you get a crust, and some of them are actually hard to remove. You have to really grind your sample window to get rid of that stuff. And it has many different names. Every researcher comes up with his own name for what it's called. One of the earliest names was the yellow stuff. Mayor Greenberg called it the yellow stuff. It's some kind of large aromatic thing. If you can, looks something like this. This is just a schematic idea of what it could contain. It's mostly large aromatic domains with some smaller side chains and some heteroatoms. Keep going with thermal alteration, you may end up at PAS, although I don't like the term PAS because to me, I'm a chemist, I'm an organic chemist. PAS are very specific things, and just to call everything PAS that you find in space to me is it's a little iffy. I'm peculiar about how you name things. So I would say there are large mostly aromatic structures. And you keep going again with more heat and more pressure, and eventually you form graphite and nanodiamonds. So the point of this is this is by no means exhaustive. This is just a quick schematic of what could happen. There are many other pathways, many other ways to form molecules. But all of this gets incorporated into some form of parent body, comet or asteroid. And in addition to that, all these processes are also going on in the same parent body. So it's very, very complex. There's turnover, there's alteration, there's all kinds of chemistry going on. But eventually, and actually pretty easily, you'll end up with something like this, some large macromolecular network. Okay, so that's what we call the insoluble organic matter. The total organic matter, of course, is the soluble organic matter plus the insoluble, but like I said in the beginning, the majority, 70 to 90%, is insoluble. You can extract the insoluble organic matter by dissolving away the rest of the meteorite in strong acids. Others have done that in the past, for example, Connell Alexander, which gives you a bulk of insoluble organic matter. You can determine lots of bulk values. Very interesting. Here's just one example out of many of what you can do with it. This is from a Chris Hurd paper in 2010 where he looked at the Tagish Lake meteorite. What's interesting here, the reason why I show this, is that different classes of carbonaceous chondrites break apart into different groups, and these groups form a trend. And these trend lines, you see, whatever you plot on these axes, whether it's certain atomic ratios or isotopic enrichment, there's always a trend, and this trend signifies alteration, thermal or aqueous alteration. So the ones that the meteorites that I'm mostly interested in are the CRs. They tend to be the most primitive, which means they have seen the least amount of alteration. So CR chondrites, and in this particular plot, they are over here. However, the bulk values are great in doing this extraction, but it's bulk, which means that there's no structural information that's lost because you have destroyed the structure of the meteorite. So you lose a sight of how heterogeneous a meteorite can be. Also, you lose the soluble organics in the process, and there's a possibility that the extraction process induces changes in the insoluble organic matter. So what I like to, one more explanation about isotopes. Why should we be interested in isotopes? Because the nanosims is very well suited at looking at isotope ratios. So just in case somebody here is not familiar with isotope chemistry, a chemical bond is a harmonic oscillator, which means you have two masses with a spring. There's a spring constant, which depends on the reduced mass of the two masses. So if you change one of the two masses, let's say you go from carbon-12 to carbon-13, then the spring constant changes, which means that the energy in the bond also changes slightly. Therefore, chemistry with a different mass proceeds at a slightly different rate than it does with the original carbon-12 mass, carbon-12 in this case. One macroscopic example that you can show is, for example, the Earth's ocean. It has a certain ratio of oxygen 18 to 16. When water evaporates, the lighter water evaporates slightly faster than the heavy water, and therefore the ratio in the ocean will change, and the ratio in the atmosphere will also change. So you end up with something that's depleted in the gas phase in 18O to a few per mil, and enriched in the liquid phase. So this is how you get isotopic enrichments or depletions. And there are many more different ways of getting to a fractionation, but that's how we can trace in a way, what happened. Okay, so the delta notation is just a ratio of ratios to some kind of standard expressed as a per mil, which means that 0 is exactly equal to the Earth-based standard. Positive is enriched in the heavier isotope, and negative is depleted in the heavier isotope. All right, that's a little bit of. This is my experiment. This is what we do. We do in situ analysis of the organic matter in meteorites. In situ means without breaking apart the meteorite. We do a coordinated approach, which means that we take one or a few samples and then unleash a host of techniques on those few samples to completely analyze what's going on there. So there's 3 phases: selection, preparation, and analysis. And we start with the selection. So, all right, this is where we get to nanosims. And if you pay attention now, then you will also understand Kota's talk, the next talk, better. So the nanosims stands for nanometer size secondary ion mass spectrometer. That means we have a primary ion, which in this case is cesium, that hits a sample, generates or sputters away the surface, generates secondary ions, which goes through a magnetic field, standard mass spectroscopy, and you can separate by mass to charge ratio. The unique thing, the nano part in the nanosims, is that we can focus our beam down to a few hundred, and at best 50 nanometer of spatial resolution. Plus we can do rastering, which means that we not only can take spot measurements, but we can actually create ion images. And we have 7 detectors in parallel, so for each spot that we hit, we get 7 signals. For example, we can set one detector to carbon-12 and the next detector to carbon-13, measure the image, take the ratio of the image, and something that is different from the background will pop out as being enriched or depleted. Okay, so here's an example of an image, something that NHON found a few years ago. And the image on the left is nitrogen 15 to 14 ratio. Image on the right is deuterium to hydrogen ratio. And you can see that it's enriched in both. This feature is enriched in both nitrogen 15 and in deuterium. So it's something organic that's highly enriched, which means that it's some kind of, organic matter that's embedded in the meteorite. So we found this one image, and this is very big. This is about 10 micrometers in length. Up until this point, we always thought that the organic matter in the meteorite was mostly some fine dusting, some fine sprinkling throughout the meteorite. But it turns out that you can also have these large veins. So we thought, well, let's try to find more veins. So what we did is we mapped a large area. So one image here is 20 by 20 micrometers, the same as you saw on the previous slide, but we did a whole bunch of them in series. And this took about 2 weeks to record. Now, Here, the point of this map is to quickly see what's going on over a large area, which means that we record at low counting statistics. We don't really care about accurate numbers. We just want to see what's going on. But we have all these maps, and so the next talk by Kota will be about these maps. So keep in mind that these maps were recorded with speed in mind and not accuracy. So what Kota will describe is some analysis that's based on, noisy data, essentially. Okay, so that's for Kota to explain. What did I do with it? I wanted to discover these veins, and for example, here, this is a small, well, looks small, but it's actually big, in my opinion, embedded organic vein of pure organic matter. There are many more, this one here, this one here. This large thing over here is a crack in the meteorite, and this over here. It's filled with epoxy. And these slices of meteorite are glued onto a substrate. But because we have nanosims and we can detect isotopes, we know from the isotope ratio that this is normal and therefore Earth-based. And these are enriched in nitrogen-15, and therefore they're from the meteorite. So it's very convenient. Okay, so that's the selection phase, and I have to speed up a little bit here. This is where the coffee kicks in. Preparation phase, I use an FIB, which is focused ion beam. This is a SEM image of the vein that I found. Focused ion beam is essentially just a lathe on a microscopic size. So you dig a hole on one side, you dig a hole on the other side. Top view, you undercut it like this. You bring in a needle, you attach the needle to the substrate, and then you lift it out. This is real time. This is me with a joystick lifting out the section. So this section is 10 micrometers by 20 micrometers, and at this point it's 1 micrometer thick. So it's being lifted out of the, and remember we saw the vein from the top, and now we're lifting out a whole section with the vein going down into it. So we should have a side view from whatever's in that vein. Okay, this is attached to a substrate, cut off the needle, and then we have to polish it, make it thinner, and the final thickness is about 100 to 200 nanometers. At this point, the section becomes transparent for electrons and X-rays, which is what we do next. Okay, another view. So this is our preparation phase. After the preparation, we get to the analysis. So we have a bunch of techniques. We do them in order because they're from low to high energy impact, but I will show the results out of order because it makes more sense. This is a TEM image. This is what that vein looks like. Again, before we had this top view here, what we saw was this. It turns out that this vein digs deep into the meteorite, and it's big. It's 8.5 micrometers. Before we had this vein, we thought, again, all the organics was sub-micrometer size. We zoom in and we see nanoglobules. That's some kind of feature that we found. We don't know exactly what they are. All we know is they're pure organic, they're round, they're sometimes hollow, sometimes not. And we see them all over the meteorite, but up until this point, we never saw so many of them bundled together. We saw an individual one here, maybe 2 over there. But this is, I cannot even count them, dozens of them bundled together. That's great. Oh, so here's some more. Here's a single. Here's a hollow one. Here's one that appears to be crushed. And we also see what we call fluffy matter, which is non-globular. It's some other kind of morphology of organic matter. Okay. The next step is we do XANES. And XANES is X-ray absorption near edge structure spectroscopy, which you do at a synchrotron. I use the ALS in Berkeley and the synchrotron in Hsinchu in Taiwan as well. And it's essentially just transmission spectroscopy, but again, this can raster, and so you get image information at multiple wavelengths. So you can do images for each. At these wavelengths, the inner shell electrons of the atoms get promoted to a higher shell. So you see the absorption for carbon, iron, oxygen, calcium, silicon. That in itself is not that interesting. But what you can do is stack these images and get a spectrum. So when an electron gets promoted to a higher shell, the higher shell of carbon is the lowest unoccupied molecular orbital, which depends on the bonding environment of the carbon. You can have a carbon single bond, a carbon double bond, carbon oxygen bond, etc., etc. And so all these form extra peaks on top of the main carbon absorption edge. And that's what ZANES is. So that's what it's really interesting for, and looks something like this. So remember that what you see here is cut off. This whole bump goes way, 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 way on, and that's just the carbon absorption bump. And these are extra peaks on top of it. And there's a lot of information here. The take-home message is, if you remember all these different structures, these different morphologies, they all have different spectra in the ZANES, which means that they're chemically different. They have different functionality. For example, here, aromatic C double bond, there's a carbonyl, carboxyl, and a carbonate bonds. So chemically, they're very different. We can do the same for the nitrogen edge, and this is actually the first time that you can see something because this vein is so large. We can integrate over a large area. The nitrogen absorption edge is very low absorbance, so we need a lot of material to get enough signal. But once we did, we could actually show there's a imide and a nitrile bond in there. So that's very interesting. Okay, then finally we do nanosims again, but this time I'll remind you once more that in the beginning we were looking at the top, now we're looking at the side of it. And what we're seeing is that this entire vein is enriched in nitrogen-15 to about 300, 400 per mil. But there's also some features that are outside the vein, like this. And there's a very small one over here. It's hard to see on this projector, but it's really there. And those are even much more enriched, up to 1,000 per mil enrichment. There's also enrichment in deuterium, but unfortunately, because nanosims is a sputtering technique, it sputtered through the whole section while we were measuring, and we lost the sample. But you can still see here that some part of it is definitely enriched in deuterium. All right, here's another section. This is from GRA 95229, another CR chondrite. And same feature again. It's what I forgot to mention is here also note that the vein is very homogeneous. There's not a lot of variation in isotopes within the vein. And we see the same here as well. It's a little blobby. That's just because of the signal. It's not very strong here. But enrichment in nitrogen-15 and enrichment in deuterium here as well. So, summing up, I'm a traditionalist. I do have my conclusions at the end of the talk. So, we can detect organic matter in carbonaceous chondrites, and we show that it's heterogeneous in spatial distribution. In morphological makeup, we see different features in the TEM, in chemical composition, and in isotopic enrichment. We can rapidly scan a large area in the nanosims and detect these larger features. We can lift them out with an FIB. We can then define different carbon morphologies based on TEM images. They have distinct carbon and nitrogen ZANE spectra, which means they're chemically different. And we found that there are some spots that are very high, at least higher than we found in that big vein, but that big vein is again higher than the bulk organic matter. And so the veins are, within the vein, they're isotopically homogeneous, and which we think means that these nanoglobules were formed from one common precursor, possibly in a cold cloud environment. It's the only way to explain these nitrogen enrichments, and but they were not formed from the surrounding material, because the signature of the surrounding material is much different than what we find in the vein. And I'll end here, and thank you for your attention.